Up until this point, when we've talked about the derivative of a function, we've only been looking at the derivative at one specific point. We've used the definition of the derivative of a function f at x equals a to find the slope of a tangent line at a point a, f of a, as well as to find the instantaneous velocity of an object at a specific moment in time, as well as other instantaneous rates of change. But why limit ourselves to a single x value? The algebra we went through to calculate these derivatives would have been virtually identical even if we had done it for any x value. To show what I mean, let's compare two examples. For example 1, let f of x equal x cubed and find the slope of the tangent line at x equals 2. For the second example, let f of x equal x cubed, but find a formula for the slope of the tangent line at any x value. The first example is just like all the examples we've done previously. The slope of the tangent line at x equals 2 is, by definition, f prime of 2, which is the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h, which is the limit as h approaches 0 of 2 plus h cubed minus 2 cubed over h. We can expand 2 plus h cubed by writing it as 2 plus h times 2 plus h times 2 plus h and carefully multiplying everything out. Or, if we know the formula for cubing a binomial, we can use that. A plus b cubed is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. Either way, we end up with 2 plus h cubed equals 8 plus 12h plus 6h squared plus h cubed. I'll show the details for multiplying this out in either method, but if you're comfortable with it already, feel free to skip ahead in the video. If we use the shortcut a equals 2 and b equals h, so 2 plus h cubed equals 2 cubed plus 3 times 2 squared times h plus 3 times 2 times h squared plus h cubed, which equals 8 plus 3 times 4h plus 6h squared plus h cubed, so 8 plus 12h plus 6h squared plus h cubed. If we multiply 2 plus h times 2 plus h times 2 plus h using FOIL or a similar method, we have to start by multiplying one pair 2 plus h times 2 plus h. First is 2 times 2 is 4. Outer is 2 times h is 2h. Inner is h times 2, which is 2h. And last is h times h, which is h squared. Combining like terms, we get that 2 plus h times 2 plus h is 4 plus 4h plus h squared. And now we still have to multiply that result by one more copy of 2 plus h. There's no special mnemonic device for multiplying a binomial by a trinomial. I like to just draw arcs to make sure I multiply each term from one polynomial by each term of the other polynomial, but I've also seen people create a grid with one of the polynomials on each side to keep track of all the different subproducts. Either way, when we multiply 4 plus 4h plus h squared times 2 plus h, we should get 6 terms, since the first polynomial has 3 terms and the second has 2 terms, and 3 times 2 equals 6. 4 times 2 equals 8. 4 times h equals 4h. 4h times 2 equals 8h. And 4h times h equals 4h squared. H squared times 2 equals 2h squared. And h squared times h equals h cubed. Combining like terms, we get 8 plus 12h plus 6h squared plus h cubed. For the first example, we now have that f prime of 2 is equal to the limit as h approaches 0 of 2 plus h cubed minus 8 all over h, which is equal to the limit as h approaches 0 of 8 plus 12h plus 6h squared plus h cubed minus 8 all over h. The 8's cancel, and we can factor an h out of the numerator to get the limit as h approaches 0 of 12 plus 6h plus h squared times h all over h. And finally, we can cancel the factors of h from the numerator and the denominator to get the limit as h approaches 0 of 12 plus 6h plus h squared, and then let h go to 0 by plugging h equals 0 in and getting our final answer that the tangent line slope at x equals 2 is 12 plus 6 times 0 plus 0 squared, which equals 12. What about the process changes if we instead try to find the formula for the slope of the tangent line at any x value instead of the specific slope at x equals 2? The derivative is still the slope of the tangent line, so we'd be looking for f prime of x, where x is a variable now. And the definition of the derivative is still the same. We just use x instead of 2. So f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. And since the function is still f of x equals x cubed, f prime of x equals the limit as h approaches 0 of x plus h cubed minus x cubed over h. Even the algebra of expanding x plus h cubed is the same as it was for expanding 2 plus h cubed. There's nothing special about 2. What we did would work for any number. I encourage you to try expanding x plus h cubed using either method shown earlier on your own, and press play when you're ready to check your answer with mine. I got that x plus h cubed equals x cubed plus 3x squared h plus 3xh squared plus h cubed. If that matches what you got, feel free to skip ahead until after I show how to multiply this out. If we use the shortcut that a plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed, with a equals x and b equals h, we can get that x plus h cubed equals x cubed plus 3x squared h plus 3xh squared plus h cubed immediately. If we multiply using FOIL or a similar method, we once again have to start by multiplying one pair of x plus h times x plus h. First is x times x equals x squared. Outer is x times h equals xh. Inner is h times x, which equals xh. And last is h times h, which equals h squared. Combining like terms, we get that x plus h times x plus h is x squared plus 2xh plus h squared. And finally, we have to multiply that result by one more copy of x plus h. This time I'll show you the grid or box method that can be used to track all of the different subproducts. We start by drawing a rectangle with one of the polynomials along the top and the other along the side. I'll write the trinomial x squared plus 2xh plus h squared along the top and the binomial x plus h along the side. Because the top polynomial has 3 terms, divide the box into 3 smaller rectangles vertically so that there is one column for each term. Then, because the polynomial on the side has 2 terms, divide the rectangle in half horizontally so that there is one row for each term. The resulting rectangle is divided into 6 pieces, which we can use to track our 6 subproducts. Each of the 6 pieces corresponds to a specific pair of one term from the top trinomial times one term from the binomial. Multiplying all of these 6 pairs, we get h times x squared is x squared h. H times 2xh is 2xh squared. H times h squared is h cubed. X times x squared is x cubed. X times 2xh is 2x squared h. And x times h squared is x h squared. Combining like terms, we get x cubed plus 3 x squared h plus 3 xh squared plus h cubed. Plugging in x plus h cubed, we get that f prime of x, which was the limit as h approached 0 of f of x plus h minus f of x over h, so the limit as h approaches 0 of x plus h cubed minus x cubed over h, equals the limit as h approaches 0 of x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. Notice that the x cubed terms cancel just like the 8's canceled in the first example. Then, just like the first example, every remaining term has an h in it, which we can factor out and cancel, leaving the limit as h approaches 0 of 3x squared plus 3xh plus h squared. And again, just like the first example, we can now plug in h equals 0 to evaluate the limit. F prime of x equals 3x squared plus 3x times 0 plus 0 squared, which equals 3x squared. The whole process was basically identical. But now, instead of having just the tangent line slope at x equals 2, we can use this formula, f prime of x equals 3x squared, to find the slope of the tangent line at any x value. Just to test it, if we plug in x equals 2, we get that f prime of 2 is 3 times 2 squared, which is 3 times 4, which is 12, just like in the first example. If we wanted to know the tangent line slope at x equals 1, we can find that too. F prime of 1 is 3 times 1 squared equals 3. We could even solve for when the tangent line has a specific slope. Suppose we wanted to know when the tangent has slope 0, which turns out to be very useful. Later, we'll solve for when the derivative is equal to 0 to find out where functions have maximums and minimums. We can set f prime of x equal to 0 and solve for x. F prime of x equals 3x squared. So if 3x squared equals 0, then x squared equals 0, so x equals 0. Hopefully you can see how much more efficient it is to find the formula for the derivative of a function rather than compute the limit over and over again for each x value you might be interested in. Looking at the derivative as a whole can also tell us a lot about a function, which is something we'll be investigating soon.